Hi, Year 11. So we're going to go through the questions that asked you to calculate values by looking at circuit diagrams. So it came from the worksheet called Electricity Equations and Laws, Practice Calculations. I've drawn it a bit bigger just so that it's easier to manipulate on the video. You can see I have not used a pencil or a ruler, which is not great, but I just haven't had time to draw them out properly. But don't do what I've done. In the exam, you need to make sure that you're neat and tidy with your diagrams and make sure that your connections look nice and crisp. So we learned two laws in today's equation, so Kirchoff's laws. So we said that the sum of the current entering a junction is the sum of the current leaving a junction. And we also said that the sum of the voltage across the power supply has to equal the sum of the voltage dropped across the circuit in a loop that an electron takes around the circuit. So we've got a number of missing values. So the first thing is really I'm going to separate out the voltmeters and the ammeters in different colours. I've missed one. Just so that it's a bit clearer to you that they are measuring different things. Okay, so you will notice that ammeters, the blue circled components, are in series, so they follow the loop and electrons have to pass through the ammeter. The voltmeters are in parallel. So remember when we did the model of the circuit, so we had, I think it was Garner, had a ruler. Who else was it in the other class? I think it was Renisha, had two rulers with gloves on. So they reached one side of a component and then the other, and they compared how much energy each charge had before and after the component. And that is the potential difference, the voltage dropped or gained across the power supply or the component. Okay, whereas the current was measuring how many charges pass through a point per second at that point in the circuit. So, we know that an electron, well, we're just going to consider a charge rather than calling it electron. We know in reality that this is the positive side of the terminal, this is the negative. We know in reality that the electrons are going to leave the negative side and move to the positive. But conventional current is from positive to negative. So we're just going to say charges moving round the circuit are going to take this path, so they're going to come down this way. At this point, they reach a junction. And some of the electrons will take this first path and come back round. And some of them, when they reach this junction, will take the second path and come through these and come back. The electrons rejoin together at this junction, so some split and take this path, but once they reach here, they're going to meet back up with the ones that come to this junction. So into a junction equals out of a junction in terms of current. Okay. Now we're going to start with the more simple bit, which is the voltage. So we know that each charge picks up 3 volts. And we know that by the time it gets round the circuit, it has to have transferred that voltage away. Okay. So voltage gained in the power supply is the voltage lost on its journey around the circuit in the loop it takes. On the first possible loop, the only component that the charges move through is the light bulb. And so they can take all 3 volts. So the light bulb voltage or potential difference across it will be 3 volts. Each charge, each coulomb, gives 3 joules of energy. 3 joules per coulomb are transferred through the light bulb, so that at this point the electrons have 0 volts and they move back to the power supply to pick 3 up again and come back round. So this is 3 volts. On the second loop, we know that at this point, so an electron has picked up 3, it's come down, it's not transferred any energy yet, it still hasn't transferred any energy yet. At this point it has 3 volts to transfer. It has to get through 2 identical light bulbs, so across the entirety of it, we know that it has to transfer that 3, which means that because they are identical, they will take a 50-50 split of 1.5 volts and 1.5 volts, which adds up to 3, so that when they are here, they can return back to the power supply to gain 3 more volts. Okay. Now, we also know the equation V is equal to I multiplied by R. We can work out the resistance of the light bulbs. They're all identical, but we can work out the resistance of one of the light bulbs by looking at this first path. We have 3 volts being supplied to the light bulb when the current of 0.2 amps flows through it. And so the resistance R of the light bulb can come from this equation. So 3 volts is why we've got V as 3, 0.2 amps flowing through it when we have this resistance R. So R is 3 divided by 0.2, which is 15 ohms. So we know that each light bulb has 15 ohms of resistance. All 3 of them, because we're told in the question that they are identical. Now, we can work out the current flowing into this light bulb now, because, again, V equals I times R, we can rearrange for I is equal to V divided by R. We know that this light bulb, when it was 15 ohms, because they all have the same resistance, could only take 1.5 volts on this loop. And so we can say that I, which is measured by the ammeter, is equal to 1.5 divided by 15. Gets me 0.1 amps. So it must be that 0.1 amps was flowing into this light bulb. It will be the same for this light bulb as well. Firstly, because they're in series, and we know that the current is the same everywhere on a series loop because there's been no split. But also because this is also 1.5 volts for 15 ohms. The other way of thinking about it is by thinking about the resistance pathways. So in the top loop, the electrons only have to get through one light bulb, so one level of difficulty. In the second loop, there's twice the amount of resistance. They have to get through both light bulbs. The more difficult it is to pass through the components, the lower the current will be. So if we've got twice the difficulty, we will have half the current. And you will see that we had 0.2 amps when there was 1 lamp and only 0.1 when there's 2, which also follows. So A1 now is 0.1 amps. We've worked this one out, but the only one we've yet to work out is A2. Now we know that the current flowing into A2 has come from this top branch plus this bottom branch. Everything in equals everything out. So we have 0.2 plus from this loop 0.1 adding together, meaning that here we must have 0.3 amps. Okay, so A2 is going to read 0.3. Come on, camera, so it's gone a bit blurry. Fingers crossed it'll sort itself out in a second. Not great. Okay, but that does give you everything that you need for this one. So, moving on to question 2. I actually did this in a bit of a weird order because question 2 is actually a little bit easier. Let me just get rid of this so that it's not distracting. We'll hide that. There we go. So, in question 2, we clearly have another series circuit. There are no junctions, and so every electron is going to take the same path. Okay, so the charges are going to come out, round, and go back. Okay, now, electrons gain 9 volts when they pass through the power supply, the cell. They know then that they have to transfer 9 volts, or drop 9 volts, as they go around the whole circuit. We know that the ammeters don't take any energy, so there's no voltage dropped across ammeters. They are measurement instruments only. I have forgotten to add 2 of the voltmeters that exist on here. That's why this is no good. Sorry, I have been trying to do this as quickly as possible, but I have missed bits. So that said 3 volts, and this said V1. There we go. Okay, so let's do voltage first. That's the simple bit. We know that electrons gain 9 volts. They have to transfer that away. We are told that when they cross R1, they drop 3 volts, which means if they started with 9 and then they drop 3, at this point they have 6. We know that by the time they get across the second resistor, they have to have 0 so that they can go back and pick up 9 more. So we know that 3 plus V1 is all of the voltage transferred across the circuit, has to equal the voltage gained by the supply, has to equal 9. And so V1 is equal to 9 minus 3 is 6 volts. So this here is 6 volts, and we can list it here. Now, let's think about it again. Current flow. Current is the rate of flow of charge, so how many charges pass a point per second. There are no junctions in this circuit. Every electron takes the same path, which means that the current is going to be the same everywhere in the circuit. So if this is 3 amps, this will also be 3 amps, and this will also be 3 amps. Lastly, we can work out the resistance of R1. We know that V is equal to I multiplied by R. I can rearrange. R is equal to V divided by I. For R1, 3 volts is transferred across it. So V is 3 for this particular resistor. The current flowing into it, we've said, is 3 amps. And so the resistance value will be 1 ohm. So this is a 1 ohm resistor. Now let's think about this. If this is 1 ohm and this is 2 ohms, then this is doubly difficult to get through. Voltage represents how much energy the charge has to transfer across the component. Doubly difficult requires double the amount of voltage to be transferred across, because if it's doubly difficult, I need twice the amount of energy for every charge passing through being transferred across the 2 ohm resistor compared to the 1 ohm resistor, so it makes sense. So that was question 1 and 2. Okay, let's move my thing, sorry. So question 3, let me zoom out a little bit. Oh, can't quite fit it in, but you hopefully get the idea. So, again, I was really scruffy with my drawing. It's not great, but you'll have the right idea. You can hopefully see again that we have a series circuit of 3 resistors. We have 2 ammeters measuring the current, and we have 4 voltmeters measuring the voltage, also known as potential difference, across different components. Now, the first thing is the easiest thing, is current. There are no junctions in this circuit. Every electron has to take the same path through all 3 resistors. So therefore the current is the same everywhere in the circuit. So if I have 2 amps down here, I have to have 2 amps up here. Now, I know the resistance values, 3, 2 and 5 ohms. And I know that the current going through them is the same everywhere. V is equal to I multiplied by R. So V4 must equal the current going through 4 multiplied by the resistance of 4. The current going through this one was 2 amps because the current is the same everywhere. But the resistance was 3 ohms, giving me 6 volts. V3 will be the current going through this component 3 multiplied by its resistance. Again, the current was the same everywhere, so it's still 2 amps, but this time the resistor value was only 2. So I have 4 volts being dropped across this one. V2 comes from the current going through the component 2 multiplied by its resistance. Again, the current was the same everywhere in the circuit, but the resistance this time is 5 ohms. So I have 10 volts dropped across it. So V4 is 6 volts, V3 is 4 volts, and V2 is 10 volts. I know that whatever I pick up across the power supply, I have to transfer across my components. And so V1 must equal 6 plus 4 plus 10, giving me 20 volts. So I can say 20 volts here. V2 was 10 volts. V3 was 4 volts. V5, nope, can't even say things right. Sorry, I'm very tired. V4 is 6 volts. Okay, hopefully that makes sense and you're following through. Now, it makes sense again. The lowest resistance resistor is the easiest one for the electrons to move through, and so it's going to demand less energy. Voltage is a measure of how much energy each charge can transfer. Okay, so a volt is the work done per unit charge, measured in joules per coulomb of charge. So how big the voltage is tells you how much energy each charge can transfer or needs to transfer to get through the component, which makes sense that the highest resistance demands the highest voltage. Okay, question 4. So we have 3 cells providing 9 volts. This is a parallel circuit, so we have multiple pathways possible. Electrons can travel around this first loop through the first bulb and ammeter and back. They could take the second path, where they travel down through the ammeter, resistor and light bulb, back up through the ammeter, back to the cell. So again, just so that you can see the difference, ammeters measure current flow. So how many charges pass a point per second. Voltmeters measure how much energy is transferred across the component per charge, joules per coulomb. So the easiest thing to work out is V1, because we know that electrons pick up 9 volts and then they have to transfer that 9 before they get back round to the other side of the power supply, and the only component on the first branch is the light bulb. So V1 has to be 9 volts because it has to transfer all of that voltage across the component. We know that an electron can travel with 9 here. It transfers 4, so it drops 4 volts, meaning that it originally had 9 minus the 4 that it has transferred across. It's dropped here. 9 minus 4 is 5 volts. So this V2 must be 5 volts. So those are quite straightforward. Now, what we have is an ammeter recording that 2 amps travels down this branch. So we know that at this point there's 2 amps. What we don't know is how much current leaves the cell and how much current travels through the light bulb, because we need to know that value, because at this junction, whatever current we have flowing through here combines with this current to make A1. We have the equation V is equal to I multiplied by R. I can rearrange that for current. I is V divided by R. Now I know that on this section, 9 volts was transferred across 3 ohms of resistance. So I can say 9 over 3 is 3 amps. So I must have 3 amps flowing through this branch. These two combine together and move into the ammeter A1, meaning that A1 must equal 3 plus 2, gives us 5 amps. Okay, so for A1 we had 5 amps, for V1 we had 9 volts, for V2 we had 5 volts. It then asked us to find the resistance values of these two components. Now, resistance R is V divided by I. For the light bulb, the voltage dropped was 5 volts and the current flowing through it was 2 amps. So for the light bulb, the resistance was 2.5 ohms. For the resistor, same equation, R is V divided by I. The voltage dropped across the resistor was 4 volts. The current flowing through the resistor was 2 amps, so it's still divided by 2. It is a 2 ohm resistor. Okay, question 5. Let's have a little look. So again, I'm going to colour the different ones in so you can see the differences. We've got ammeters measuring current flow. Quite a few of those here. And then we have voltmeters measuring the voltage or potential difference across components. Okay, hopefully you can see that we have three paths that electrons can take. There's the first loop, where the electrons flow from the power supply through 2 ohm resistor and back. The second path through R1 and back, and then the third path through this light bulb and back. Now, we know that whatever is picked up across the power supply has to be transferred on the loop that the electron is on. And so we can see that because this voltmeter reads 8 volts, it means that we must have picked up 8 volts from the supply. Because you gain 8 volts and then you drop 8 volts and then you're back to the other side of your power supply. That then tells us that each electron that comes on the second path also has 8 volts to drop across the component, which means that this must also be 8 volts, as this one must also be 2. Okay, now we know that we've got current flowing into each junction. Into each branch. The junctions are here, so where the splits are. So we've got current coming out of the power supply. At this point, it splits into current flowing in the first branch and current coming down here, which then again splits later into this section and this section. The current from the bottom branch and the second branch recombine at this junction and flow into A2. And then the current from A2 recombines with the current from the top branch at this junction flowing in here. So we can see that all of the currents from each branch have recombined by this point. So the total current from the supply has to be 12 amps. So we have 12 amps of current all the way round until this point where the current then splits. So if we have 12 amps in, we know that into a junction equals out. So we have 12 in must equal A1 plus whatever current I have here, which is equal to 3 plus A3. Okay, because those are the currents that are splitting later on. Okay, we also know that A2 has come from the 3 amp and the A3 value of amp. Okay, so A2 is equal to 3 plus A3. So those are things that are known. We also know that V is equal to I multiplied by R. I can work out, because I have the voltage dropped across this component and its resistance, I can work out what A1 is. I rearrange my equation. I is V divided by R. The voltage dropped was 8 volts when the resistance was 2 in this section. And so 4 amps must be flowing through A1. Okay. Now, I know that 12 was coming into this junction. 4 went down this pathway, which would mean at this section here, I must be left with 12 minus 4. I must have 8 amps flowing down here, okay, because I had 12, 4 split into this branch, I have 8 moving down. 3 move into the second branch, 3 amps, and so what I have is 8 has split into 3 plus A3. So I must have 5 amps travelling through this ammeter here. So A3 must read 5 amps. 5 amps will flow through this section. And now at this junction, the 3 amps from this branch plus the 5 amps from this branch recombine, so I must have 8 amps at A2. I can check this because 8 and 4 from this branch are then going to recombine and make 12 amps. The last thing I can do is I can work out R1. R is equal to V divided by I. R1's voltage was 8 volts and the current flowing through it was 3. Getting me 2.7 ohms. So that gets me all my values for 5, and then we've got one more to do. Again, let's colour our ammeters and our voltmeters so that we can see the difference. Ammeters are measuring current flow through the circuit. Voltmeters are measuring the potential difference across components. Okay, so the simplest one I can see to start with is that whatever current flows into the power supply has to flow out. So if I have 8 amps of current at this point, I've not had any splits until this point, so A1 must also be 8 amps. Okay, I can see that at this junction the current is going to split, and some will go down this path and some will go down this path. I can see that 3 of the 8 amps went through the first branch. So I must have 8 coming in minus 3 leaves 5 amps flowing down. So A3 will read 5 amps and A2 will also read 5 amps because nothing has happened to split the current between those two. We can then check because the 5 amps coming up here will meet the 3 amps coming in here, and 5 plus 3 makes 8, which matches what we've got so far. To find V2, V is equal to I multiplied by R. V2 has 3 amps multiplied by R1. Okay. On the bottom branch, V3 is equal to I multiplied by the R value of 3. I've got 5 amps multiplied by 4. Okay, that's 4 ohms. Gives me 20 volts. So I know that I've dropped 20 volts across this component because 5 amps flowing through a resistor of 4 gives me 20 volts. I also know from my law that whatever I pick up on the supply, I drop on my loop that I take. So if I've gained 20, I drop 20. So I know then that this must also be 20 volts because it has to pick up 20 to then transfer 20. And again, on this pathway, the only component that I'm going through is this resistor. So this must also be 20 volts. So now I have the value and I can rearrange for R1. Okay. And I've got about 6.7 ohms for that one.